Our next presentation comes from another Nobel laureate, Professor Stephen Chu, Professor of Physics, Molecular and Cellular Physiology, and Energy Science and Engineering at Stanford University. As I'm sure you know, Professor Chu served as the 12th US Secretary of Energy and has long been a global leader in advancing clean energy solutions. He has also been a member of the ADIA Lab Advisory Board since its inception, and a great supporter and trusted source of wisdom of ADIA Lab, for which we're deeply grateful. Today, in his third symposium keynote in as many years, Professor Chu will tell us more about the challenges and opportunities of getting to net zero greenhouse emissions. Professor Chu will help us deepen our understanding of the latest advances in energy storage, electrical vehicles, and carbon capture, and will also discuss what's often known as the elephant in the room, the growing energy demands of AI. Please join me in welcoming Professor Stephen Chu to the stage.
So I asked if I could use my presentation instead of the one there. Is it possible? No, it's not connected. Can I connect this one? I just made it up. It's not connected. Can you plug something in?
I think we'll have to present what's there, probably. Or we can see.
I can't hear. No? Anyway, okay. In that case, I'll do what I can do, and when I get to the thing I want to add, I can do something else. Okay. So let me talk about what the challenges are for getting to net greenhouse gas emissions. I want to first remind you that the temperature of the Earth, average temperature of the Earth has been warming up since 1850, and the first UN goal was 1.5 degrees, and you see on the right-hand side, upper right-hand side, that's 1.4, 1.6 degrees. So we're in the process of passing 1.5 degrees as we speak. One of the first speaker talked about, well, the market will respond to what's happening, but there's a problem with that, and the problem with that is what is happening is not what's really happening. Now let me explain this. 90% of the additional heat that is trapped by the greenhouse gases goes to the oceans. The oceans are 70% of the surface area of the Earth, and it's the surface area of the land and the ocean that determines the weather. However, a considerable fraction, over half of that energy, actually goes into the deep oceans that don't affect the weather. The oceans are very cold, they're 2 degrees. The ocean time is, mixing is very slow, and so what we really see as the additional heat trapped in the oceans doesn't actually come to the surface and make our weather for periods of time from decades to perhaps a century. So how do we know this? Well, we actually make measurements. These are not computer simulations, and this profile gives you the excess heat in the ocean from 1960 to 2024, approximately. The light blue is the stuff at the surface of the ocean from 0 to 300 meters down. As you go darker in blue, you go deeper. And now the upper blue, 0 to 300 meters, mixes well enough with the surface temperature of the ocean and land that it does affect the weather on a weekly, daily, monthly time basis. But you go just a couple hundred meters down, and what you find is the time scale becomes 10 to 100 meters. And if you go even deeper than that, and if you go even deeper than that, you're looking at tens to decades. So that's the problem. It's that slow mixing time. Now, how do we know about this mixing time? It is not a computer simulation. There are large uncertainties in computer simulations, and unlike satellite data, you can't take measurements of it by just looking down. And so what we do is we use things called Argo flows. So these are these little yellow things. They're battery powered, and they're tossed overboard. And they bobble around the ocean. They go down, linger for a couple of kilometers. They measure salt, they measure salinity. They go down to 2 kilometers. The newer generations are capable of going all the way down to 6 kilometers, which is deeper than the average depth of the ocean. And then every 10 days they come up, they radio home what they found in salt, salinity, where they are, using GPS. Now, you might think that one of these or 2 of these things aren't going to tell you what the ocean's doing, and you're quite right. You need a lot of them, and I didn't have this, but there are about 4,000 of these deployed around perhaps 1 degree everywhere in the oceans. And so they're just bobbling around, scattered everywhere. And it's that knowledge that has told us what is happening with the oceans. Another thing that you've probably noticed, sometimes what you notice is not what you really get, but as someone who is a physicist and it works in statistics, some of the things are true. And this one is that you probably may have noticed that you can get very wet years and very dry years. And we call this hydroclimate volatility. And it's been now, since the mid-century, the volatility of going very dry, very wet is increasing. So we call this a whiplash effect. And in fact, it was this whiplash effect that was the cause that primed the LA fires that devastated much of southern Los Angeles. They had a very, very wet year. A lot of weeds grew up where nothing really grows. And then a very dry year, so all of a sudden those weeds were just prime tinder material. And so an ignition caused a great wildfire. Some good news, the price of solar, wind, even shallow offshore wind is declining below that of natural gas. Natural gas, of course, depends on where you are. If you're in a place like Abu Dhabi, the price of natural gas is not very high. But the United States' natural gas is also not very high. And if you compare the cost of natural gas, total levelized cost of the natural gas peaker and the cost of the gas, and you compare it to solar, hydro, wind, we find that it is now more expensive. So that's good news. This levelized cost means it's the cost of the CapEx investments, the cost of the operation, the cost of everything all rolled in over the lifetime of the asset. In wind, there's been phenomenal progress. These are 2 Chinese companies that are building very large wind turbines. The one on the top is 25 megawatt, a single turbine, 25 megawatts. The diameter of the rotors is over 300 meters, 3 soccer fields. Okay, just digest this. And these are built for onshore and offshore. Offshore is a little easier because you can put things on a boat, and onshore you have to negotiate turns. The one on the right is a 50 megawatt offshore turbine, 50 megawatts. The standard of the industry is about 15 megawatts, by the way, just so you're wondering. These are built to withstand 150 mile-an-hour winds, typhoons, and still be floating. And so and the reason they're building such gargantuan ones is because they found that the economies do scale. The wind gets cheaper. I'll skip that and just go to what renewables really cost. Wind doesn't blow all the time, sun doesn't shine all the time, so the full cost of renewables includes enhanced transmission distribution systems, and it also includes backup generation, just in case the wind stops blowing for a week or 2, which has been known to happen. So it's the cost of the backup systems, which is an additional cost to the renewables, the intermittent renewables. If the renewables are only 10 or 20% of the cost, it's a nothing, the stuff is already there. But when you go to 50, 60, 70, 80% all renewables, intermittent, then energy storage becomes huge. California is now about 70% carbon-free energy, of which 60% are renewables. And so we actually have to deal with this every day. And it requires a careful planning, careful coordination in order not to throw that electricity away. So energy storage is key. This is a picture of my favorite battery. It works in the following way. When you have a renewable, an intermittent renewable like wind, you do the energy intensive thing. You pump water. And when you need it, you open up the valve. Pump storage is 95% of all electrical energy storage in 2015, but things are radically changing now because of the technology of utility scale batteries. And here I give you a timeline between 2015 and 2024 of pumped hydro storage. Pumped hydro storage is increasing, but grid scale batteries is growing like topsy. And so by 2024, it was 69 gigawatts, down from essentially 1 or 2 gigawatts by 2015. And China right now, who happens to be the biggest installer of renewable energy, wind and solar in the world, actually it's comparable to all the rest of the world combined, they're also the biggest installer of battery storage for utility scale. And so they're planning on about 180 gigawatts of battery storage. It's mostly short-term storage, only 1 or 2 hours, 2 to 4, that's it. So you're not storing for 2 days. You're storing to peak load shift only. This is an example in California, May 23rd, 2024. Yellow is solar. So during the middle of the day, we have an abundance of solar energy. Blue is hydro, and all the other colors are either we import energy in purple or wind or so on and so forth. So you see in the middle of the day, we're producing an excess amount of electricity, which you either have to export or store in a battery or throw away. And so we didn't want to throw it away, and so in order to take advantage of this, we started building lots of batteries. I might also add that the blue hydro, even though in the middle of the day when you're producing an excess amount of power, you still have to keep the hydro dams going, because if you shut off the hydro dam completely, you kill the river and the fish. So that's ecological constraints. So what has California done? In the last 2 years, we put in 16 gigawatts of batteries. And so in this plot here, where you see that dip, you're producing solar's coming in strong, you're producing excess solar, and as you go to 5, 6, 7, 8 o'clock at night, you begin to generate lots of power, peaking up to 5 gigawatts worth of battery power as you ramp up. So what you've done is you just shifted the load from noontime to where you need it the most. Why do you need power at 6 p.m. or 8 p.m.? You need it because that's the peak of air conditioning. It gets hottest around 4, 5, 6 p.m. Anyway, so this keeps us from throwing away the power, but it also changes economics, because during the noontime, the price can be better than free. You can get money by taking electricity. And that has opened up a huge opportunity for energy arbitrage, because as the batteries come down, you're buying electricity at zero cost or negative cost, or you can buy battery power at night if you have 12-hour storage, and then sell it for EVs at 10, 20, 15 cents a kilowatt hour. So it's tremendous profit. As I said, China is really pushing ahead with this. They're also the leader in utility scale batteries, and they're pushing ahead with numbers that dwarf what we did in California. Battery storage for EVs is climbing very rapidly. This is a plot of energy per unit volume on the y-axis, energy per unit weight on the x-axis. Both are important for EVs. If you fly drones, then energy per unit weight is everything. This is my prediction 5 years ago, that this is where I thought batteries would be in 5 years, or by 2030 actually. I was wrong. I know that because I'm on the board of a battery company selling batteries at 550 watt-hours per kilogram. Those batteries are being used today in drones. They're high-end batteries. They don't have to last 1,500 times. In some applications, maybe twice. Never mind that. The cost of batteries is going down. We've established what's called a learning curve. A learning curve is defined as every time you increase the amount you produce by, let's say, an order of magnitude, the cost goes down by a factor of X, a certain percentage. Then another order of magnitude, the price goes down another factor of X. So when you plot this cost versus production on a logarithmic curve, you get a straight line. And here you see this straight line down here. Once you've produced enough, And what we found is when you're producing enough batteries for EVs, the price of lithium batteries is plunging dramatically. Comparing 2020 to 2020, 2030, 25, 2030, you see it's plunging rapidly. What disrupts the learning curve? You get disrupted if something else changes. And in this case, the something else that could change are really materials demands versus material supply. Nickel and cobalt have gotten so expensive that people have already transitioned over to lithium iron phosphate batteries. The iron phosphate doesn't have high enough energy density, high energy density. It's high enough, but not as high. And but it still works, and it is safer. So nickel and cobalt are being phased out. What about lithium? There are ways of extracting lithium that have been developed. I have a couple of papers on that, but what is happening is you can take salty water out of the ground, and you can just take out the lithium and pump the rest of the dirty water back in the ground. You do not have to expose it, evaporate a big lake worth of polluted heavy metal water with radiation. And so people are beginning to do that. And so doing, the stores of lithium will be better, and they will last for perhaps hundreds of years, maybe longer. Copper, also, there's an issue. Copper will be running out of copper, which you don't run out. What it really means is you go to lower grade ores, it gets more expensive, and you look for substitutes. We do have, in principle, a substitute, and that is we have massive amounts of carbon in the ground. All the stuff that we take out of the ground, the most is the following: coal, natural gas, oil, and rocks for concrete. That's it. And so there's so much carbon in the ground. If you can turn some of that carbon into high conduction nanotubes that would be cheap, then in terms of conductivity per unit weight, you've done better than copper. And it doesn't find its way in the atmosphere. So we need conversion of materials, and we have to look at the materials we have the most of. EVs have gotten much better. Teslas, this is a Model 3, $45,000 for the long-range Model 3. It's got a pretty decent range, 350 miles. The batteries have gotten so good that you can go on 175 miles in 15 minutes, which means if you want to go 100 miles, it only takes 5 minutes. Its acceleration is more than what most people need, 0 to 60 in 4.9 seconds. There's a competition growing. Xiaomi, a cell phone company, decided they thought cars were really like cell phones with wheels. And 4 years ago, they made a decision, now we're going to make cars. And boy, did they make a good car. For $42,000, you can buy a SU7 Max. It's got a much longer range than the Tesla. It's got 219 miles in 15 minutes, 0 to 60 in 1.98 seconds. I test drove one of those things. I test rode one. I didn't drive it. The flesh in your face is pulled back, literally, just like you're being launched in a rocket. Why you would want to accelerate like that, I do not know. You can snap your neck off, or your passenger neck, if you're not careful. They developed their own motor. Their highest end motor is a special steel. It's stronger than highest grade submarine steels because the motor turns at 27,000 RPM, so the centrifugal force doesn't rip it apart. And it weighs 42 kilograms, 578 horsepower, and 42 kilograms, and it's this big. Okay. The CEO of Ford Motor Company said it was the best car he's ever driven in his life. All that for 40,000 miles, $40,000. Okay, so and they've got better ones out, and the electronics are much better. This actually has LiDAR as well as cameras, so its self-drive is actually much safer. Anyway, it's also a good-looking car. Why is it so good-looking? Well, they actually took the body designer from Porsche and said, why don't you come here and design our car for us? Okay, let's talk about data center energy. Data center energy is climbing like crazy, and Bloomberg New Energy Finance says that it's going to increase. It's 35 gigawatts today, 2024. It probably will increase to 78 gigawatts by 2035. And so that means the fraction of electricity used in data centers will go from 3.5 to 8.6%. Why is it doing this? It's because it's driven by artificial intelligence and machine learning, the number of parameters they're using in order to get to improved ChatGPT versions or Geminis or whatever you use. ChatGPT had 1.8 trillion parameters, 2 times 10 to the 25 floating point operations a second. ChatGPT 5 is using 5 times that much. The latest the average exascale data center is 200 megawatts, but they're going to 2 gigawatts per data center. So, in fact, what's the rate limiting step? They can't buy gas turbines fast enough. This has had political repercussions. In December 2024, the capacity prices in the area of the United States, Pennsylvania, New Jersey, Virginia, West Virginia, Ohio, so-called PJM territory, the capacity prices went from $1.25 to $11.25, a 9x increase. And so people were calling for resignations, riots, things like that. Virginia has 10% of all the data center electricity used in the United States, even though they're not blessed with hydropower or anything. They just want business. I should say, I was preparing slides, I was looking at Bitcoin. Bitcoin is 30% of all the data use, Bitcoin mining. And in Bitcoin mining, you create value by solving a stupid mathematical problem. So proof of work, putting some hashtags on some number, you get a coin, but it's energy intensive. And there's another thing trying to emerge, but the word is that is not yet going to take over. And the reason ChatGPT gives is why Bitcoin is going to remain in lead and proof of scope would not take over is because many financial people think when you're really spending energy, that really means there's value in it. So this is what the finance community is telling us. and so for that reason, Bitcoin still remains the dominant type of mining. And again, 30% of all electricity being used. The major applications, need I remind you, it's money laundering and tax evasion. And we just got a convicted criminal who, for money laundering and tax evasion, get pardoned by the President of the United States, and now he and the President are in partners with Bitcoin, or Trump coin. All right, even with cost-effective utility-scale batteries, possibly hydrogen, don't have time to talk about it, the world will still need compact turn-on sources of energy, and so that means we'll still need natural gas or coal, or if you use carbon, you do have to capture and sequester or use the carbon, or nuclear fission with spent fuel disposal. Nuclear fission, don't confuse fission with fusion. Fusion is very difficult. There are right now scientific experiments, and the best estimates of when it will be commercial, not when it breaks even scientifically, but when it will be commercial, would be somewhere between 40 years and never. Let me go back to fission. Right now, China is building, this is a little out of date, they're right now building over 30 nuclear power plants, followed by India, Turkey, South Korea, Russia. The United States is not seen on this list. If you build nuclear power plants below $4 per watt, since they now believe the new generation could last 80 years, you're in the money. And so China has figured out how to build nuclear power plants on budget, on time. They're pretty safe. If you burn anything, the small particulate matter gets in your lungs, and you get heart disease, stroke, lung cancer, COPD. If you compare the deaths of deaths per terawatt hour generation of electricity from burning coal, burning coal, burning wood, burning anything, nuclear is far safer. Nuclear is way down there. It's a little safer than wind. People fall off wind towers. It's a little more dangerous than solar. Falling off a roof isn't as dangerous, I guess. But in any case, it's 100 times safer than burning biomass, and it's considerably safer than hydropower, but dams break. The good news of nuclear, the newer designs the target is walk-away safe. Walk-away safe means you lose your power, you lose your electricity, you lose access to water. In fact, you cannot control the power plant at all for whatever reason. Then the thing will not melt down. It will not contaminate. And the idea is that once the nuclear reactions are stopped, there's enough, you put the whole business in a big pot of water, and it just doesn't overheat enough to melt down anything. So just the thermal inertia prevents it from contamination. The small modular reactors are easy to make walk-away safe, and in fact, they can be made so you don't even have to refuel them for 6-7 years or so. Repositories is an issue. These are conventional tunnels. In Sweden and Finland, they've solved their nuclear disposal agreements. The people in Sweden and Finland have approved these plans. These are very elaborate tunnels to go underground to put the waste. You put the waste in there. After it's all there, you seal up the tunnels and say no one comes in anymore. It's permanently sealed. There's a better way of doing this that's being tested, and that is you can use borehole drilling. You can go down a couple kilometers and go sideways a couple kilometers, and you can put the nuclear waste in these boreholes. This gives you access to many more geological sites that would be stable. It means you don't have to transport the nuclear waste very far. And the difference in cost is the difference between human spaceflight and spaceflight using probes. There's a world of difference when you have to maintain safety of human beings. And so it could be that deep borehole drilling would be a solution. It's especially important in a big country like the United States, where you have to ship the radioactive waste across state lines, and the people in states that don't have nuclear reactors don't want nuclear waste crossing their borders and then going somewhere else. And so they will protest this. And that is a problem. That's an unsolved problem. Military, U.S. military does ship radioactive material across state lines, but they have a technical secret. They just don't tell anybody because it's under national security. But we can't do this for civilians. So in any case, let me just finish by saying there's another problem that's still unsolved. And that problem is that the production of food, we use fertilizer. Fertilizer does have greenhouse gas emissions, but even if you green up the production of fertilizer from greenhouse gas emissions, the mere fact that you put the fertilizer on the field and the fertilizer that's not absorbed by the plant gets turned into N2O. Nitrous oxide is a greenhouse gas 300 times worse than carbon dioxide, lasts 100 years. And so as the world uses more and more fertilizer, which it will use, this becomes a bigger and bigger problem. And it turns out that food production and food waste is roughly 25% of greenhouse gas emissions around the world. So this is not a small thing. It's a big deal, and it's due to the nitrous oxide. This is how it breaks down agricultural soil management, but if you also include manure and those things, it's maybe 80% of greenhouse gas emissions. I already said that, 300 times worse. There's a potential solution, but it has to be tested, and it's using the ability to put multiple genes into microbes, and these microbes can be then engineered to enter into symbiotic relationships with plants. Proof of principle was a company called Pivot Bio, partnered with Zymergen. I was on the board of Zymergen. We developed microbes that can feed corn, eliminate half the fertilizer. That was good. Bad things that took 8 years because we only could put in one gene in at a time. And that long development time was too slow and the company went bankrupt. In my lab, I'm trying to figure out how we can put in 10 genes at a time. 10 genes at a time, progress is combinatorially faster because the solution requires about 10 genes, but you've got to figure it out. You can type up the genes and synthesize them. That is not the problem. It's actually getting them into the cells. And so maybe this will work, maybe not. Finally, I just want to mention cost of carbon dioxide is a huge amount of carbon dioxide. It'll take us 50 years, 80 years, I don't know, to get rid of all the carbon emission. And so we're going to need to capture carbon dioxide. There are a number of novel ideas that could greatly lower the price. Two of my colleagues at Stanford developed one on biochar they think is much, much better. We've figured out a way, we think, that could use electrochemistry to make it much, much less expensive. Air capture at maybe $100, $150 a ton instead of $500, where it is today. Remains to be seen whether those things will work, but we do need them. And so with that, I'm not going to talk about that, but with that, I'll stop. Thank you.
Thank you, Professor Chu, for the compelling presentation. We will take a quick question from the audience before we go to a break.
There's a
Hi there. So throughout your presentation, you've mentioned a lot about how China is going ahead of the US. And so is it just because China is China? Or
yes.
Or is it because or is it the private industry that's pushing ahead of the US in China?
The companies I talked about are private companies. They're not state-owned companies. China has followed U.S. playbook. The U.S. playbook of 100 years ago and maybe 50 years ago is they take things invented in Europe and science and discoveries invented in Europe and they industrialize it. And so automobiles, Benz Motorwagen, internal combustion engine cars, they made cars better in U.S., better, cheaper. So that's what China's doing. They took things invented in the United States and in the West, and they're industrializing them. But like the United States science got better, China's science is getting better, and so China's science in material science and a few other fields is ahead of U.S. now. But they're still good at industrializing things. These are all internal investments within a private company. We used to, in the United States, we used to be able to deduct 100% of research and development off company profits. Some time ago, I think in the current administration, I'm not sure when, but around that time, it went away. And so I'm trying my best to get it to go back, that if a company will want to invest 100% of some of its profit into R&D for future projects, they can do that and get a tax write-off. You want to encourage companies to invest in themselves, especially now since the U.S. government hasn't figured out what it wants to invest in. Well, it has, but it's not investing in this stuff. It's not investing in the green technologies.
How do they incentivize it?
How did the Chinese
how do they incentivize?
Well, I think it's the Chinese companies are ambitious. They want, the United States as a government did not incentivize Ford Motor Company to do something. Henry Ford had a dream. T.J. Watson had a dream for computers, and they had a long-term vision. And what has happened in the United States is that long-term vision is no longer there. They're being pressured by what's your last quarter's profits. The long-term vision of where the company wants to be in China is still alive and well. That's a major difference.
Thank you once again, Professor Chu.